Hi, in this video we will see how to find the response of a damped mass spring system excited by various conditions. The governing equation is m double dot x plus c dot x plus kx equal f. F is the output force. M double x is the acceleration. C x dot is the force applied by the dashpot, and the kx is the force applied by the spring. Actually, this governing equation, we could write it to express the acceleration with respect to the various forces, and we get double dot x equal f minus c x dot minus kx divided by m. So using various blocks, we will build our model piece by piece, and we start from a function x. We get the dot x by differentiated with respect to time. Then we multiply x dot by a constant c using an amplifier, and we multiply x by k, and we sum the two to get the first expression, cx dot plus kx. Donc here we have the differentiator and the amplifier. From x we get dot x, we multiply by a constant, and at the same time we pick up the signal x, we multiply it by k, and we use this block which sums the two entries. If we add the external force, if we get if we add the external force F, and we use another block to calculate the sum of F and minus Cx dot plus Kx, then we use an amplifier with a gain of 1 over m, we get F minus Cx dot minus Kx divided by m. This expression actually is the acceleration. At the same time, the acceleration could be obtained from x dot by differentiated with respect to time. So this output should equal the output from the differentiator here. And actually, working with the integrators is better than with differentiator. Why? Because in the former, meaning with the integrators, we could use the initial conditions, which gives better control on the solution obtained. So we will transform the differential, or instead of using differentiator, we will use the integrator, and the model becomes this. It's exactly the same. To implement this on Simulink, we will need the following blocks. We need 2 integrators, 3 amplifiers of different gains, 1 oscilloscope to observe the response, and 1 constant. We will start by a force equals 0 or 1, and 2 blocks to calculate the sum. We will start by wiring all these blocks together, and we obtain this model. Actually, I will switch to Simulink to see the result. Welcome back. I have built the model on Simulink, and I have connected all all the inputs, all the blocks. Okay, for the time being, we need only one input, which is connected to X, the response of the system. And actually, I don't need two controls to calculate the expression f minus cx dot minus kx. I could use only one control. So I will double click on the control and I will say that it has three inputs. One is is plus, the other two are minus, and I will get rid of this one and then connect if we need to recover any parameter, for instance x, and to work with it in the workspace, in MATLAB's workspace, we could send it with this control, which is called to workspace. And actually I get an object from in the workspace, which has two components, mainly two components of interest to me right now. The first one is called out.tout, which is the time simulation, and x is whatever parameter I choose here. It will be the displacement of the system. So we will start by investigating the response of the system to a zero output force. So what is the response of the system to an initial condition? Of course, the system at t equals 0 shouldn't be at rest, otherwise it will remain at rest. Therefore, I will change the initial conditions so that the initial velocity it's 1 meter per second, and the initial displacement is 0. I double click on the oscilloscope and start the simulation. And I could see, in fact, for in the case where there is no damping, here I have a damping of 0, I get an oscillation at the natural frequency. Now, if I change the damping, I put, for instance, 2, and I double click on the oscilloscope and start the simulation, I will get the damped response of a mass spring system. Actually, what I could do is to go back to MATLAB and see, in fact, that in my workspace there is an object called out. If I type it out, I see it's a Simulink object and has two variables, t out and x. So I could, for instance, plot. I should use the object out dot t out dot x. So I will plot the out dot x with respect to out t out, and I get exactly the same response as expected. So I will go back to Simulink to continue our demonstration. Now what I will do is consider a force, a constant force of, for instance, amplitude 10. So my system will be excited by a constant force. Actually, I will start the simulation, and I see that my system, in fact, oscillates around F over K, which is the displacements obtained if we apply a force F on the spring of stiffness K. And in this case, F is equal 10, K is 100, so F over K is 0.1. Now we will start considering variable forces, and we start with a sinusoidal force. I click on library browser and look for sources for sine wave or sine source. I get rid of the constant and plug the new force, sinusoidal force. I will add another input to the oscilloscope in order to see the force being applied. I double click on the scope and start the simulation. And here, in fact, what I get is a combination of the response due to the sinusoidal force and the initial condition. And here I can see the transient response, which is quite present at the beginning of the cycle. If I change the initial condition, I type 0 velocity, the transient response will still remain, but it will be very, very weak. Let's move to a different force, namely the step function. I'll drag and drop the force. I get rid of the sine wave and plug the new force. I double click on the step function and say that the step function starts at 1 second and the final value is 10. So in fact, after 1 second, we will apply a constant force of, for instance, 10 Newton. I double click on the scope, start the simulation, and observe the behavior of the system without initial conditions. So this is the force. It's 0 before 1 second. At 1 second exactly, it will be applied and the force will be constant. Instead of looking for other sources individually or combine some sources, as we will see later to produce special forces, we could use a signal generator, which can generate different type of signals. So the signal could be sinusoidal, square, sawtooth, random, etc. I will first connect the signal generator. I get rid of the step function before continuing. So I will apply a square signal with amplitude 10 and a frequency of 1 radian per second. I double click on the oscilloscope as usual and start the simulation. And here I can see the form of the force. It's a square force, and the response of the system due to this force. Another interesting source in Simulink is the waveform generator. In fact, it enables to define analytically multiple signal expression and choose one expression as output at a time. So let's plug the waveform generator and connect it to the model. I will create two signals. The first, it's a combination of two sinusoidal waves, one of amplitude 10, frequency 1 radian per second and without phase. And the second, actually there are two ways to express the same thing. I will multiply the signal, the sinusoidal signal, by 0.5 and keep the same amplitude, and the frequency will be 2 radian per second. And the other way on, in fact, is to say here I have 5, 10 times 0.5 is 5, and have 1 in front of sign. We get exactly the same result. This is my first signal. I copy it, and the second will be the same signal plus a pulse which is of amplitude 10, starts at t equal 2 seconds and lasts for 3 seconds. And right now the output signal is 1, meaning I will be applying to my system this signal, a combination of two sinusoidal forms of different amplitudes. The first one is 10 and the second is 5, and two different frequencies. Now let's see the response of the system. Here we are. We start the simulation and I get the response to this combination of forces. Well, we could in fact improve the smoothness of the applied force. All what we have to do is go to the waveform generator and increase the sampling frequency. So the delta t between two moments, we will reduce it from 0.1 to 0.001. And I launch the simulation and we will see that the input force is much better, much smooth. Now, to see the response due to the second expression, all what we have to do is to choose as output signal the second expression. Okay. We start the simulation. and we see the combination of the two signs and the impulse, which starts at 2 seconds and lasts for 3 seconds, which means it will disappear at t equal 5 seconds. Actually, this expression could be obtained differently, but as we say, the hard way. I will draw the equivalent combination of blocks which gives exactly the same force, and I'll come back. So to produce the same signal, we need two sine waves, one of amplitude 10 and frequency 1 radian per second. The second will be of amplitude 5 radian per second and a frequency of 2 radian per second. A step function which starts at t equal 2 seconds and lasts forever, of course, because it's a step function. And the final value, the constant value, is 10. And we add to create the pulse, we create another step function which starts at 5 seconds, and the final value will be -10. So after 5 seconds, the sum of the two will give 0. We double click on the scope and start the simulation to see, in fact, that we get exactly the same results. Well, other sources exist in Simulink, but we have seen the main ones in this video. You are advised to start using Simulink and discover all its capabilities, and it's quite rich.